Good morning. Welcome to our first kind of alone time since we're splitting off the 111 students. So we're on our own now. So just 101. So we are gonna be doing this for the rest of the semester. So bright and early. Remind me never to do this again. 9 o'clock earliest for now on to the future, right? Starting next semester. So we can go ahead and get started. Just continuing off kind of what we did last time. You have enough information to finish the homework. We've covered everything that's going to be on that. But one thing that I do want to talk about before we move on to talking about atoms is a few important points about conversion factors. We're going to see that for many of the things that we're going to talk about later on in the course, there are going to be two main ways of approaching a variety of problems. So you're going to have kind of, and some work best for certain people. Some you're more familiar with, you're more comfortable with. But we're going to see that with these two ways, you can use either one. You're going to get the right answer. But in my opinion, one of them is a little bit easier and might be a little bit less stressful. But we'll see. We'll see. There's going to be two approaches that you're going to deal with when solving problems. And so one of them is going to be using formulas. And so a lot of students do feel comfortable using formulas. This is what you've been kind of using in high school, middle school before. I tend to not like formulas. The reason for that is because, it's so silly to just memorize a string of letters and, maybe some numbers in there as well. But, that's my opinion. And we're going to see that sometimes, you may like using formulas. And so, for example, you might have something like this. This is the density formula. That's the Greek letter rho. It's not a P, but it's kind of a P. R-H-O. There we go. And it's essentially a formula that's just telling us, if we, want to relate these three quantities to each other, we can do that by using this formula. We can say, okay, the density is equal to the mass over the volume. And that's one way to do it, and it'll work. But if you're going to be doing like multi-step dimensional analysis, this is kind of something you'd have to solve beforehand and then move on later. The way I like to do it, but again, you're totally free to choose whichever way works best for you, is just kind of treat everything like this as a unit conversion. For example, let's say you have a density equals to, I don't know, let's say it's something like, you've got a number like this. And hopefully by now, having at least looked at the worksheets, you might be more familiar with conversion factors being anything that has more than one unit, right? And so let's say if we were to do this formula, let's say we got 0.789 grams over 1 ml or something. We could solve that and get our density, and that's the number we get, right? But what might be another way to look at it is to say, well, this is really just a conversion factor. And we can use these things as conversion factors, or we can use them as formulas. So let's say, for example, we have this this density idea. So density, again, is a ratio of something's mass to its volume. You know, that old story, whatever, about the pound of feathers versus a pound of bricks thing, right? They weigh the same, right? They're both a pound, but the feathers, of course, are going to take up way more space. And the reason for that is because they have a lower density. A brick has a higher density. And so let's just take a look at this, and then we can talk about density some more. So let's say that I have 204 ml of a substance with a density of 2.21 grams per milliliters. What is its mass? So, two ways to approach this. Option one, use the formula. And we can do that. We can say, aha, well, density is mass over volume. I mean, this one, it's an easy formula, right? It's 3 letters. And in fact, this one's even easier because, let me just write it a little bit differently. Density is love. It's just a heart. Ta-da. Okay, but anyways, that aside, we can say, okay, well, we can plug these things in and get our mass out. We can say, okay, well, I have this density that's 2.21 grams per mil. Well, that's equal to some mass, whatever that is. That's what we're looking for here, right? And we have a volume that's 204 milliliters. And so we can go ahead and solve this. So remember, gram per mil is the same thing as gram over 1 ml. So we don't need to write that in. Hopefully we can just solve this. We would just multiply the two together. I don't know where my calculator is. That's always good. So I'll use Google. Okay, so what am I doing? 2.21 times 204. And we get 450.84. Looking at these numbers, they both have 3 sig figs, so we're going to want to route our number to 3 sig figs. Notice our unit will be grams. The milliliters cancel out, so we're going to get grams here. So we can use the formula. Works just fine. All right, alternatively, we can say, aha, well, I have this idea of density, which tells me 2.21 grams equals 1 ml. By the way, the density is going to be different for each substance, so it's not a kind of fixed conversion factor. And in fact, it does vary with temperature, but by and large, stuff that I give you, you know, it's going to be just, here's a number, use it. So that's what this means. So again, same thing as density. It's a conversion factor. So we can set it as an equality before, and that means we can put it either way. We can say 1 ml over 2.21 grams, or 2.21 grams over 1 ml. Well, you know, whichever way we want. We can go between those two, just like any other conversion factor. If we're going from centimeters to inches, we can put centimeters on the bottom, inches on the top. This way now we can see, okay, if we're going from milliliters to grams, we're going to probably use that one on the right there. And if we're going from grams to milliliters, we'll use the one on the left. So either way. So let's go ahead and do it. So we're starting with our measured quantity, 204 milliliters. And we're going to say, okay, well, we want milliliters on the bottom, so it cancels out. So we're going to put the gram part on top. And lo and behold, we end up getting our same answer. So it works either way. And that is all well and good. So just, again, whichever way makes the most sense to you, you're welcome to do that. So have fun with it. So just keep in mind, though, a lot of these things you don't ever need to memorize formulas for if you can work the units properly. So, for example, another common conversion factor that we'll see later on is something called R. We're going to see this in the gas law chapter. It's called the universal gas constant. It comes with the units, a whole bunch of units that we have not seen, except perhaps liters and Kelvin there. But this conversion factor, if you wanted to derive a formula from this, you could, just by looking at the units. You don't know what those units mean yet, but you could do that. Or you can use it as a conversion factor. So you can say, aha, well, I've got, all these different units. Let's see what I can do with them. And you can work with things like this. Or specific heat capacity. This is another one we'll see. A lot of kind of constants that are important for us, like the density for a given substance, will have complex units like these. And so you're going to be given formulas for all of them, or you can just work with them as conversion factors. And so we're going to see these many times throughout the course. So again, it's going to be kind of your choice. I would probably stick to one way, whichever way you choose, just so you don't get confused. I do think the using just the units is better, but that's my opinion. So I'll leave it at that. So we'll see. There's going to be many more later on that you're going to see that you can use either way with. So these were, just so it's in the notes, these were future conversion factors that we're going to see in the course later on. Or, another one, negative 3,200, kilojoules per mole. These are all common conversion factors that we're going to see. So I'm just throwing out numbers for some of these, but we're going to see these all the time. And so if you really want, again, you can use them. You can use formulas, or you can use them as conversion factors. So cool. Okay. So we're going to see that the density of something is a conversion factor, or you can use a formula to work with it. It'll be very useful because many times in reality, if you're dealing with liquids, for example, no one wants to go measure those out using a scale, a balance. A lot of time it's a lot easier to just measure a liquid volumetrically, so you'll just pour a certain amount of liquid, and that way you'll know how much mass you have. Just a little bit easier that way. So we do see density a bit when we're talking about calculations. So just keep that in mind. All right? So there we go. That's kind of the last bit that I wanted to talk about with things like this. All right. Any questions on kind of this idea? Alrighty then. Let's talk about atoms. So we are now starting, I guess, chapter 3. I don't remember if this one's split into 3A, 3B, but we're starting the first one, if there's a second. I don't think chapter 3 has a A and B, but I could totally be lying. No, it does, because we have atoms and then compounds. Okay. Anyways, let's talk about atoms. So, as we've kind of mentioned, I don't know, in the first day or something, atoms are kind of the smallest unit of matter. And I don't mean unit as in like meters or liters or that kind of thing, but kind of the smallest chunk that we can do. Um, this was a concept devised by the Greeks way back when, where they're like, well, if we keep taking this piece of pure substance, whatever it is, and keep breaking it in half, eventually we'll end up with this idea of an atom, and we can't break it up anymore after that. And so it's kind of our smallest chunk of matter that we can have is one atom. And again, this is probably something you've talked about in middle school or whatever, but we'll go over it anyway. Atoms are made of three things. What we call subatomic particles. And let's switch colors because why not? Those you've heard before are the proton, the neutron, and the electron. So these are the three particles that make up all atoms, and as we know, all atoms make up everything that's made of matter. So again, mostly everything. So it all comes down to these three. There are other ones: neutrinos, positrons, antiprotons. Those are kind of less important for us. These are the three big ones. The other ones, come out of nuclear chemistry or are like randomly emitted from quasars or something. So they're not really going to be super useful for us. So for us, normal matter is made of these three substances. And we can talk about them. So one thing that distinguishes these is they all have a different charge. A proton has a positive 1 charge. So protons are positively charged. Neutrons are neutral. They have no charge. And then electrons have a negative 1 charge. That's going to be kind of our main way of talking about them, because when they were first discovering the existence of subatomic particles, the easiest way to kind of distinguish them was their charge, because we knew a lot about electricity. Not really. We knew something about electricity at the time that these were discovered. We knew about charges. We knew that these things would be able to attract each other, positive and negative attracted, and negative repelled, positive repelled, right? So we knew those ideas, and so we were able to kind of identify that these existed using the idea of charge. So that certain ones would repel each other, therefore they have the same charge, and certain ones would attract each other, therefore they had opposite charge, and some wouldn't react at all, meaning they don't have any charge. So, with that, we can also talk about their mass. So, matter all takes up mass, right? Or they all have mass. A proton has a mass of about 1 atomic unit, AMU, atomic mass unit. A neutron also has a mass of about 1 atomic unit. So protons and neutrons are almost mass, they have the same mass. Almost. They're very, very slightly different. And is that, yeah. And electrons, by contrast, have very, very small amount of the mass. Actually, I think there's another 0 here. Yeah, one more 0. Yeah. So, very, very small. We often will consider this negligible, because we see, no matter how many electrons you have, generally we're going to see it's the same number as protons. The mass of electrons is not even within the ballpark of the mass of the other two. And so we're going to see that when we're talking about atomic mass and all that, we're really only looking at protons and neutrons, because the electrons weigh so little. They're so much smaller than the others. we also know that the protons... Oh, shame on me. I'm being inconsistent with my colors. Oh well. Protons and neutrons are both contained within the nucleus of the atom. We'll talk about that in a little bit. And then the electrons are actually zipping around about the speed of light in orbitals around the nucleus. So you might have seen this kind of idea before where, we've got this nucleus and we've got these kind of rings around and there's electrons in them zipping around and whatever, that one's going that way. You might see something like this. This is what's called the Bohr model. And it's largely been replaced by more sophisticated models. I'm going to erase our little arrows here. But for purposes of kind of, our first look at atoms, it's a pretty good place to start. So we have here the nucleus. And then we have the electrons. Kind of just in this one it has it in orbits, meaning those electrons are just circling it. We know the patterns are not circular anymore. So we're going to see later on in chapter 4, actually, next chapter, a little bit more about how we now know about how electrons move around, the patterns that electrons can kind of occupy around the nucleus. But for right now, we're just getting our foundations in. We can go ahead and say, yeah, the electrons are kind of spinning around the nucleus there. So hopefully nothing terribly new here. Should be somewhat familiar with it. All right. We're going to see that we can talk about these particles together. First things first, let's start with protons. We're going to see that... Actually, let me give you a couple of examples, and we'll look through it together. So... Okay. Sorry, just give me a sec to draw these. Okay. So I can't really draw the protons and neutrons because they're all just going to be clumped up in the nucleus, so I'm just going to tell you how many there are here. Actually, this one should be 4. And I'm going to go ahead and write a few things about this. So, I'm going to go ahead and tell you these are all lithium atoms. And so, we're going to see that we can talk about these subatomic particles. They're all lithium atoms, but I've changed a few things in the second 2 cases from the first one. As we can see, there's one thing that's the same with all of these. And hopefully we can figure out what that is. I'm gonna make our electrons just a little bit different colored, just so it's a little bit more obvious. There we go. If we look at what's the same, we see that in all 3 cases, the number of protons is the same. And we see, okay, well, we've got this idea that they're all lithium atoms, Perhaps there's some relationship there. But let's go ahead and look at the rest. Just to, let's see what's happening with all these. If we look what's different between the first and second ones, well, it looks like the electrons are the same. I see 3 electrons around that nucleus. I see the protons are the same. The neutrons are different. And so what's different about these? Oh, well, I mean, these numbers appear to be different from each other. Those numbers probably are significant, but I don't know. So perhaps the neutrons have something to do with that, because that's the only thing that's changing, right? But again, let's keep looking. All right, well, so let's compare now the first one and the last one. Well, it seems like the protons are the same, neutrons are the same. Bringing us back to that 6 thing again. So, again, that's probably something to do with neutrons, but we'll look anyway. Well, it does look like we have this thing that is different in the lithium here, in this lithium. And what do we notice as well is we are missing an electron here, right? We had 3 in the left one. We only have 2 in the right one. And we end up with this plus here for some reason. So, revisiting our idea again, okay, well, the protons are all the same. And these are all lithium, so I think it's reasonable to say that all lithium atoms have the same number of protons. And indeed, this is true. In fact, all atoms of whichever element you're looking at will have the same number of protons. We're going to see that hydrogen atoms have 1 proton, helium atoms have 2, lithium have 3, iodine have 53. I might be mistaken about that, but carbon has 6. We have a term that we can talk about called the atomic number, which is given by the letter Z, is going to be equal to your number of protons. And if we take a look at any periodic table, let's say we're looking at helium, we're going to see that helium, in fact, here, let's switch over to our periodic table. Aha, notice all of these things have a number. In this case, they're in the top left. Oh, good, I was right about iodine. We're going to see that number is the atomic number, and that tells us how many protons we have. So, for example, if we look at chlorine here, hopefully you can see where I'm circling, on that right-ish, top right-ish, we see that it has the number 17. That means that every single chlorine atom has 17 protons in its nucleus. If we look at bismuth down here, every single atom of bismuth has 83 protons. Xenon, 54. Neon, 10. So, that atomic number tells us the number of protons that we have. Sometimes it's centered on the top. In this particular periodic table, it was on the left, but typically you'll see this number, in fact, you'll always see this number on your periodic table with any given element. So, this is what distinguishes one element from another one. So again, we've in the past defined element as everything having the same type of atom. Now we can say more specifically that an element is defined by the number of protons in its nucleus. And so that's what we'll see here. All right, another color. How about light blue? We saw this idea of the 6 and 7 comparing our atoms here. We have a term for those as well. We might call these lithium-6. These are called isotopes. I don't know why I capitalized it. We don't typically capitalize elements. I guess it's the beginning of a sentence, but whatever. We talk about these, and we read them lithium-6, lithium-7. We call them isotopes. And we see here that otherwise they're identical except for the number of neutrons. Right? We saw the protons the same, electrons the same, but the neutrons were different. And we see that isotopes these will actually be neutrons. That determines if something is, or determines what isotope you have. For example, you probably have heard in popular culture, you have a couple of isotopes of uranium. Uranium-235, that's the one you can make bombs out of, or you can make, nuclear energy out of. And uranium-238 is the more common one. That's the most common isotope of uranium, but it is non-fissile, so we can't use it for nuclear chemistry. Those are two isotopes of uranium. And we're going to see that some elements only have one stable isotope. By stable, I mean not radioactive, but that's not something we're going to cover in this course, so just accept it. Accept the word stable. And some have 20 stable isotopes. There is no pattern here, really. We're going to see there kind of is a pattern, but again, not something in this class. Let's hop over to Wikipedia. Alrighty, let me see. Let me switch this to Wikipedia. Window capture. Yes. Aha. Okay. Wikipedia. Let's take a look at the element silver. So I'm going to actually zoom in here just because I realize a lot of you may not do it. But look here. We have this little box, main isotopes of silver. That's where I'm looking on this side. We see, we have those numbers up on the top left of the element symbol. Silver is Ag. That's its element symbol, argentum. We have two stable isotopes here. So if you're looking in nature, you're going to be able to find silver atoms that have what's called a mass number of 107 or 109. So this one has two more neutrons. This one here has two more neutrons than this one. And for whatever reason, those happen to be the ideal numbers for silver. For whatever reason, 108 is a radioactive one, so it's not stable. It'll break down by itself. So silver has two stable isotopes. How about we look at cobalt? Another element. Let's look at the same thing. Cobalt only has one. Cobalt is all 59. So all these other ones are synthetic. So they don't exist in nature. Only cobalt has just one. How about platinum? Hopefully this has a bit more. Yeah. We have 5 isotopes of platinum. So each element can have a whole array, and these two differ by 1 and they're both stable. But if you take one away, it's not stable anymore. This one's stable though, but then not the one that's 2 below it, and the one 6 above it is stable. There's not really a pattern for us to figure out here. So we don't need to worry about it. But just suffice it to say, some atoms have more isotopes than others. And that's all right. No way for us to tell, at least at this level. And so you'll see that some have many more, some have just one. Like the cobalt just has 1. Silver had 2, platinum is 5, whatever. Doesn't matter. But we're going to see that only certain combinations are kind of acceptable. So, for whatever reason. But let's take a look at that. If we take a look at that, those 2 examples that we saw here, we see that this number up top, this is what's called the mass number. And let's go all the way back up here. Perhaps we can see how to get that. How might we get this? Well, perhaps these numbers directly above have some manner here. And indeed, we can see, if we add the protons and neutrons, we're going to get 6 and 7 for those left 2 cases. And indeed, we'll get 6 on the right as well. So, we're going to see here that the mass number is going to be equal to the number of protons plus the number of neutrons that you have. So you add those up and you get what's called the mass number. So if we have that silver isotope, it was 109 and 107, right? We can ask ourselves now, okay, well, I've got this silver 109, and I can say, how many neutrons does this thing have? Well, it's a good question. We know that the number of protons plus the number of neutrons is 109. We have 2 variables here. Do we know the number of protons in silver? Well, remember, a number of protons is the same for every element, and it's right here on the periodic table. We just have to find it. And so it's generally a good idea to kind of get familiar with where some of these things are. Silver happens to be right here. And so we see it has an atomic number of 47. So we can say, 47 plus our neutrons is 109. And therefore, the number of neutrons is 62. Yeah, that looks right. And so we can see that this isotope of silver has 62 neutrons in its nucleus. So, good stuff there. Notice we got this from the periodic table. So we got that from the periodic table, and so we have our number of protons there, and so we can just use subtraction to get our number of neutrons. So, there we have it. We can see how many neutrons something has looking at its mass number. Notice something, by the way. If we take a look at silver, notice, if you remember from just a moment ago, we saw that, hey, silver comes as 107 and 109. We saw that in Wikipedia, right? Those were the two stable isotopes of silver. But we don't see that number anywhere on this, right? We see, oh, well, we have this 107.868. What's that? Well, that's not 107, that's not 109. It's in fact closer to 108 than anything else, and we saw that 108 was not something that's existing in nature. So, where did that 108.8 come from? Or 107.8 come from? Why is that number on the periodic table, but not the 107 or 109? Well, I'll tell you. This thing, the 107 and 109 are mass numbers. Those correspond to just the number of protons and neutrons in a given atom. So in the 107 we have 60 neutrons, in the 109 we have 62 neutrons in those silver atoms. We're going to see this 107.8, which is on the periodic table, is what's called the atomic mass. And you might say, well, what the heck's the difference? The atomic mass, we're going to see that it doesn't make sense to talk about individual atoms when we're actually going to be using them. It makes a lot more sense because we're going to see later on, a teaspoon of water has quintillions of water molecules in it. And so does it ever make sense to talk about a single water molecule in kinds of practical sense? No, it doesn't. And so we're going to see that this is kind of the mass on average of a silver atom. And more formally speaking, that is the weighted average of all isotopes will give you the atomic mass. So I closed Wikipedia for some reason. Let me pop it open again. Okay, one sec. Let's get that back. Okay. Back to Wikipedia we go, and we were looking at silver. Okay, isotopes silver. We might actually have this. Let's see. Do we have... Okay, well, whatever. So, notice, well, these proportions are almost half and half. And our atomic mass is somewhere in between the two, right? And it's in fact a little bit closer to 107. And indeed we see, well, 107 is the majority. And so we're going to see here that by kind of looking at these numbers, we're going to be able to figure out the atomic mass. I'm not going to ever have you calculate it, but I'm going to show you where it comes from. By the way, apparently there are 28 isotopes of silver. Go figure. Or radioisotopes. So that means radioactive ones. So there are 30 isotopes of silver. So go figure. Anyways, that have been found, though apparently most of them are, not, less than 3 minutes They don't exist very long. Anyways, I'm gonna just copy these numbers down. We have 107 and 51.839%, and then we have 109 and 48.161%. Okay. All right. So back to seeing me. A weighted average is, again, not something you're going to have to do, but it is essentially what you do is you'll take the, here, I'll give you a formula. Not something we're going to use in this class. I'm not going to have you calculate this. It's going to be the isotope mass times the abundance. The sum of all of those. So, I know sigma notation can be a little scary. It just means that you do this for every single one and add them all up. So, for us, for silver, while the isotope mass is actually slightly different from the mass number, I'm going to just use the mass number here. So, we're just going to kind of cheese this calculation. Again, not something you're going to need to do, but I'm just showing you where this number comes from. I'm using the percentage in decimal form here. If we do this math, 107 times 0.51839 plus 109 times 0.48161, we get 107.96. If we look at our atomic mass is 107.8, close enough. So the difference is there because the isotopes don't actually weigh 107 and 108, or 107 and 109. They actually weigh slightly different numbers, but we're kind of estimating, and that's why we're going to end up getting this number that's somewhat close to our atomic mass. So that's where that number comes from. And it's the weighted average. So if you were to say, okay, well, I'm going to weigh out 3 million silver atoms, not very many, and we're going to see on average, they're all going to weigh 107.96. Some will weigh 107, 51% of them in fact. 48% will weigh 109, but on average it'll be 107.96. We're going to see that number is important later. But that's the number you're going to see on your silver here. So you'll typically see, I'm going to just use I'm going to use our calculated number because I don't want to scroll up. This is the atomic number. This is this element symbol. And this is the atomic mass. Again, nothing about the mass numbers here. Nothing about the isotopes. It just is the atomic mass. So it's the weighted average. If we remember, cobalt had just one isotope that was stable. 100% of cobalt in nature is cobalt-59. Let's go ahead and look at cobalt. And let's see. Aha, it's 58.9331. And that's going to be the actual mass of cobalt-59. So the mass number tells you protons and neutrons. And we're going to see that actually protons weigh slightly less than neutrons do. And so that difference is why this number is not exactly 59, 58.9. So that's the reason for that. So it's because protons weigh just a little bit less. So we'll be cool with that. Okay, enough about neutrons and isotopes. Let's look at the last case. Wow, we've really done a lot. Okay, there we go. The last case here. Aha, well this is the missing electron case. And we ended up having this positive thing on this as we went through. Okay, we'll take a look at that. we're going to see that lithium-6, written this way, is an atom. If we have a charge on it, that makes it what's called an ion. So an ion is a charged atom. And that means that the number of protons does not equal the number of electrons. So for regular atoms, they are equal. You take a look at the periodic table, you find your platinum, it's got however many protons, it has the same number of electrons. But we're going to see that the vast, vast majority of chemistry happens when electrons do things. We're going to see that oftentimes electrons will leave atoms, or they might come and join an atom. And so we're going to see that we can end up having charged atoms, which we call ions. Specifically, we have two types of ions. We have cations, not cations, but cations. These are positive ions. And we have anions, which are negative ions. We can say this lithium plus is a cation. It has a positive charge. And let's see what we can, if we can figure out how to get that number. Well, we saw that when we had the same number of protons and electrons, their charges cancel out. And so we have a 0 here. We don't typically write that. You might see that later on if you're talking about transition metal chemistry. That's something you do in Gen Chem 2. You might put a 0 there, but not for us. We as chemists, we don't like to put redundant information. If nothing's written, it's assumed to be 0. All right, but you see we have written something. We've written a +1 up here. That's, again, we don't like the numbers that are extra, so if it's just a positive, we assume it's 1 positive. And we see here that, we actually have 1 less electron in that ion form of lithium. And so we can see that the charge of an ion is the number of protons minus the number of electrons. And we can see that, well, this lithium here, 3 protons, 2 electrons, is +1. And so we'll indicate that by putting it up top. If we take something like sulfur, I typically write E-, but that's just electron because they're negatively charged, right? Well, the charge of this one will be -2. And so the way we'll write this is S2-. I don't know which isotope this is. I'm just using it as an example. We're not really worried about the isotope right now. Chemists typically will write the number first and then the sign of the charge second. So we see that this way is not the way that we're going to write it in chemistry. For whatever reason, they've written the magnitude of the charge first instead of second. So we don't write it this way. We write it that way. You'll see biologists. In chemistry, we can write something like this. Biologists sometimes write it like this. You might see something like that in biology class. We don't do that either in chemistry. So, sorry, you're going to have to stick to the way we do it here. So, we always put the, if we're going to indicate a charge or something, it's going to go in the top right, and it's going to have the number of the charge, if it's not 1, and then the sign of it after. Okay, so that's how we're going to be writing these things. Alrighty, let's do a couple. Oh, one more thing, actually. Let's be a little bit more formal here. For example, this calcium. I need to check, what is calcium's atomic number? 20? Yeah. This is how an element symbol might look if you want to put all the information we know about it. This is something that's called AZE notation. No, I'm sorry, the Z goes on, but what am I saying? We just talked about this. For whatever it is, an A is not atomic number, it's mass number. Z is atomic number, because why not? And E is the element symbol. So we're going to see this is the mass number. That's protons plus neutrons. This is the atomic number, which is just protons. Here's your element symbol from the periodic table, your abbreviation for the element name. And then here, if necessary, you'll have a charge, which is protons minus electrons. I can fit that. So, all this information we can get from this. Let's see, with this example of the calcium, 2+, let's see if we can't figure out what all the subatomic particles are going to be for this substance. If I give you a symbol like this, we can figure out what those particles are going to be. Hopefully there's one that's the easiest to do. Protons we can do right away, right? We can say, aha, it's just that same number right there. That number. Or if we really wanted, we could say, okay, well, I don't trust this symbol. I'm going to go look on the periodic table. But if it's given to you on the bottom there, it's going to be the correct one. But if you go on the periodic table, you look up Ca, calcium, you're going to find that it has an atomic number of 20, which means 20 protons. All right, neutrons then. Well, if we look on the right side here, all this information we have information about protons. We have information about neutrons in the top left number. Okay, so we do that. We see we have protons plus neutrons there in the top. So we know we have our mass number, protons plus neutrons. We have 20 protons. And so n in this case is 20. If we wanted, actually let me use green for this one. We can say, aha, if I just subtract those two, I'll get that number. That's how we got neutrons. And now the last bit, electrons. Well, we have a charge of 2 plus. We know that charge is protons minus electrons. And so we have a charge of 2 plus, or positive 2, since now we're talking about an actual number, not the symbol. We have 20 minus our electrons, so if we need this number to be positive 2, we are going to have 18 electrons. All right. Oops. Any questions on that one? Whoops. Alrighty. Now let's do another. Okay. If I give you these three, can you construct the element symbol? Or rather the this like AZE notation thing, which I'll just call the element symbol, but can we do that? Yes, we can. So we need a couple of things here, right? First things first, we should probably find out what element this is. So head over to our periodic table. We're looking at number 24. Aha! I have found it. 'Tis chromium, which is Cr. So we have our element now. We know it's chromium. We know it's going to have a 24 in the bottom left, because that's where we put our atomic number of protons. And so, okay, we are missing a couple things. We need a mass number and a charge, if we have those. We do have enough information to get a mass number. And we would just need to add these two together. We're going to say, aha, that's 54. We just added them together. Apparently I've made an isotope of chromium that does not exist, because we saw that 59 was the only one that exists for chromium, but that's okay. This is a fake exercise. Alright, and then we have the last thing we need to do is the charge. Remember, charge, protons minus electrons, 24 minus 26, which is negative 2. So we say 2 minus on this one. Hopefully this makes sense with the idea of the charge of the atom. We say, aha, well, we have 2 more electrons than protons. We have more negative stuff, so our charge should be negative, right? Same thing with the other case, where we had fewer electrons. We have lost some negative stuff, so we're going to be more positive. And so you can kind of think about it as well. It's always a good idea to kind of make sense of the information you're given. And so that's kind of something to think about. I can write that out, I suppose. We're going to see that negative ions, which we call anions, they have gained extra electrons from something. We're going to see later when we talk about electron transfer reactions how something like this might work. If you think about it, they are more negative. they have gained extra electrons. Electrons are negative. So we're going to see that things have gained electrons, they become negative. And we're going to see the opposite, cations, which are positive. These ones have lost electrons, and they've given it to something else. And those are therefore more, or rather less negative. So they've lost something that's negative, and therefore they become less negative or more positive. Either way you can say it, right? It's the same thing, you're just reframing it, positive versus negative. So, I mean, it'd be weird to say less positive for the first one, but more positive for the second one makes sense. So, alrighty. How are we feeling on that? Any questions on those? Cool. Yeah, hopefully nothing too crazy here. Simple math, adding, subtracting, you can do those. Alrighty, that's honestly as far as I wanted to get today. So I guess we'll end a little bit early, which is great. We all like that. So yeah, we're good. So what day is it? Today's Tuesday. On Thursday, we will continue on now talking about compounds. Now that we've talked about atoms, we're going to now bridge this into compounds, start talking about things with multiple atoms. We'll talk about some things we can do with those on Thursday, I suppose. All right. If any of you have any questions, throw them in Discord. Have fun. And don't forget your homework is due, I think, Thursday. So make sure you're working on that. And we'll go from there. So I'll see you on Thursday then. Enjoy your couple of days. Enjoy learning about these atoms. And we'll start with compounds on Thursday. Great. All right. See you later.